This is a quick review of the Laplace transform. A quick review. This is no substitute, no replacement for a proper course on Laplace transforms. This is just the preamble, the preface, if you will, to the lectures on how to use the Laplace transform to analyze electric circuits. I dedicated this set of slides to the memory of Charles Schultz, who put a big smile on my face as a child every Sunday morning. Do you remember those days in elementary school when you learned to add and to subtract? It was so easy, eh? But soon enough you were introduced into the wonders of multiplication and division, and right then and there you started missing addition and subtraction. How easy it was to add and to subtract compared to multiplication and division. And you may have dreamed of years if there was a way of transforming multiplication and division into addition and subtraction. Well, there is a reality to that. You can replace multiplications by sums and divisions by subtractions, but how? Transformation. What kind of transformation? Logarithms. You transform the operands into their logarithms. Do you remember doing this? Logarithm of a times b times c is equal to the sum of log a plus log b plus log c. It is as if we had transformed those two multiplications into two additions. Do you also remember this? Logarithm of a divided by b is logarithm of the numerator minus logarithm of the denominator. It is as if you had converted this division into a subtraction. Well, logarithms today and yesterday. Today, to find a logarithm, we use a calculator. We only go and press the right button for logarithm base 10 or base e, and we have instantaneously a logarithm with 10, 14, 24, 50 digits of precision. But until not too long ago, until 1974, every engineering and science student and every engineer in the field would have a little booklet, and in that booklet called the logarithmic tables, you would have a column with numbers and a set of logarithms corresponding to that number. For instance, you want to know what is the logarithm of 501? You look for 50 here, and on the top the 1, and down here at the intersection you say the logarithm has a mantissa of 0.6998. That's the way. And that's been like that since John Napier or Nepper introduced log tables back in the 17th century, right? He published logarithmic tables. So right after he invented logarithms, and that were pretty much like that, a column with numbers and another column with the logarithms. So if we have to multiply 73 numbers like a times b times c times 70 other numbers, what we do is we go to the log tables, we look up the corresponding 73 logarithms, and then we add them together by paper. And once we have the addition of all the logarithms, we look up on the table what number it corresponds to, and that's how we find the product of those 73 numbers. Let's do that again with simple round numbers. To multiply 3 and 4, take the log of 3. The log of 4, yeah, I know, the right numbers are 0.4771 and 0.6021. And then what? And then you add them together, the two logs, and look up that sum, 1.0792, into the lookup tables, and you get that that corresponds to the number 12. That's how you would multiply using logarithms 3 and 4. Is it a transform? Is the logarithm a transform of sorts? But it would be so much cooler if we could transform derivatives into multiplications and integrations into divisions. That would be way cooler these days, right? Because after all, we have calculators that multiply and divide. These would convert differential equations into algebraic equations. That is what we want. Well, with the Heaviside operator we've seen in the previous movie, we did sort of that, didn't we? However, today we will visit the way Laplace does the same, and he does it much better because he includes the initial conditions, as we shall see. Numbers, functions, well, logarithms transform numbers into numbers. But the Laplace transformation takes a function of time and turns that into a function of a new variable s that is called the complex frequency, with a real part sigma and an imaginary part omega. That is a complex frequency, that is the Laplace variable. We go from the time domain, our universe, into the Laplace domain, which sometimes I think of as another universe, the Laplace universe, the frequency domain. We take a function of time f of t, this one, and we transform it to the Laplace domain as f of s. That is, the Laplace transforms pairs because they correspond to one another, right? They are the left and the right. The imaginary part of a complex frequency omega represents an oscillation in the time domain, and it's given in radians per second. It's an angular frequency. And the real part of s sigma represents an exponential decay in our universe in the time domain. It comes in 1/seconds, which is the same as radians per second anyway. How do we differentiate in the frequency domain? Well, when we differentiate in the time domain, in the frequency domain we just multiply by s. That's what we do. Sweet. We have converted, or actually Laplace did convert, a differentiation in the time domain into a multiplication by s in the frequency domain. An integration? Well, when we integrate in time, as here, the corresponding transform f of s gets divided by s. In that sense, we could say Laplace turns an integration in the time domain into a division by s in the frequency domain. And you think, well, wait a second. We've seen a movie not too long ago on Heaviside's p operator, and he did sort of the same thing. df dt, pf, integral of f dt, f over p. Isn't that the same? No, because you see, Laplace includes the initial conditions. When we take a pair f of t and f of s and we integrate in time f of t, in the frequency domain, sure, we multiply by s, but we also subtract the initial value of f of t. F at 0 minus in the time domain. Remember, that is just a number, right? It is the initial value in the time domain of f of t. An integration? Well, when we integrate in the time domain, like here, in the frequency domain, in the Laplace domain, we divide by s, and we add this function of s, a constant divided by s. Remember, that is a number. It is an integral, right? The integral from t equals minus infinity, from the beginning of the universe to right before we closed or opened the switches. We accumulate all of that effect, and that is the number we put on top of s, and add that to fs over s. What is the plan now? Well, the plan is we will take the differential equation or equations that describe the behavior of an electric circuit, give them to the Laplace transform for it to transform them into algebraic equation or equations, solve those algebraic equations, and then transform back that solution to the time domain. That's the plan. Transform back? How? How? How are we going to do that? Well, you see there is an integral inverse Laplace transformation which we will not use. We're not using that. What we will do is we will use lookup tables of transforms. We use them and we look up for the transform of the function we obtained, and then we find what is a corresponding function of time. That is pretty much what we were doing with logarithms back before 1972, right? Because now we don't do that anymore because we have computers and calculators. Can we not do the same Laplace thing with a calculator? Well, yes, you can with the HP 50G and very advanced calculators like those. But let's suppose you can't, and that is the purpose of this set of slides. That is on plan A. Let's review the plan. To solve a system of differential equations, what we really want is the functions of times y of t, the solutions in the time domain. The way we will do it from now on is we transform that system of differential equations, this one, using a Laplace transform into a system of algebraic equations in S in the Laplace domain. And then we use algebra to solve that system of algebraic equations and find their solutions. But the solutions are now in the Laplace domain, right? Y of S. And then we use lookup tables to transform them back to the time domain, which is where you and I will use them as engineers. A little bit on notation. You see here is a function of time, f of t, and this weird L parenthesis represents apply the Laplace transform to f of t. And what do you get? Uppercase of f's, the Laplace transform. That represents Laplace transform of f of t, same as what is on the right hand side. More notation. That is the Laplace transform f of s. This represents find the inverse Laplace transform and you will obtain f of t. And that is the inverse Laplace transform of f of s. And that has been that quick review. Now let's enter into a whole nother chapter, essential functions. You see, of all the possible mathematical functions of t, engineers have special interest on a few. Let's review those few very quickly, beginning with the unit step, also known as the Heaviside step function or just the Heaviside function. Is this one? That is a unit step. Let's describe that in detail. Before 0, that u of t is 0. But at 0, that is 1 already, and after 0, it continues to be a 1. Remember, before 0 is 0. At 0 and after, it's 1. That is a unit step. The shifted step. Well, it's the same step, u of t, that has been shifted to the right. It has been postponed. How do we do that? We write u of t minus a, any a of your choice, and the u of t will shift to the right by a seconds. That shifted step is 0 for any point in time before a, but at a and after a, it will be 1. Bingo. The most interesting part here, I think, is to remember the notation. U of t minus a shifts the unit step to the right by a seconds. We'll remember the rest. Another one, also with the step, the inverted step. You say the inverted step is 1 all the way from minus infinity up to and including t equals a. But after a, it will be 0. In equations, u of a minus t, please observe the notation, right? So u of a minus t, so we are shifting the inverted step is actually identified by this negative t, and a is the shift, right? A minus t, shifting a seconds to the right. That is 0 if t is greater than a, so after a. but at a and before, that is 1. That is the interesting part here, this notation. Same as before, u of t minus a was a shift to the right. Now u of a minus t is a mirroring on the time axis and shifting to the right as well. Another function, the pulse, also known as the gate function. Which function? This one, right? This one. That function is 0 before 0 and it's 0 after a given g, which is the width of the gate. But between 0 and g and including them, it's 1. P of g of t is 1 between 0 and g, including 0 and g, and it's 0 elsewhere. We will use that pulse or gate function to sample a segment of a curve that we want to include into some description of a complicated function of time. Multiply that gate function times any expression you have, and you will be cutting out everything that is not between 0 and g. The shifted pulse. It's added power to the gate function, to the pulse. You shift it to the right by a. Replace t by t minus a. Same deal we did with the shifted u. U of t, replace t by t minus a, and you shift it to the right. Okay, pg of t minus a. Same with g, but now it starts at a. It doesn't start at 0. Same deal. That pg of t minus a is 0 before and 0 after, and it's 1 between and including the ends, the edges, the ends. Now the ramp. This is a ramp. The ramp is 0 before 0, and then it's a ramp after 0. The ramp, r of t, is 0 for t less than 0. And then after that is t. Okay. And the shifted ramp? Well, that is not the shifted ramp, right? This is a shifted ramp. It's shifted to the right by a. Again, we have replaced t by t minus a to signify we're shifting the ramp to the right by a seconds. That shifted ramp is 0 before a, and it's a ramp, a shifted ramp, t minus a at t and after, at t equal a and after a. The inverted ramp? Well, just replace t by a minus t, and you will have an inverted and shifted ramp that is non-zero before a and it's 0 after a. We say that is 0 for t after a, the end of the ramp, and it's going to be that inverted ramp, that decaying ramp, a minus t, for t less or equal, less than or equal to 0. The last of this illustrious parade of famous functions favorite of engineers, the impulse, also known the weirdo function. Well, consider that. Let's introduce it that way. Consider that you have a pulse, a gate function that has a width a, check it out, between 0 and a, and it has a height of 1 over a, not 1. I'm asking you, what is the area under the curve of this pulse? You say, oh, that piece of cake. Width a multiplied by height 1 over a, that is 1. The area under this pulse is 1. And I ask you, you say, okay, consider that now you make that pulse half as narrow, half as width, half as wide, but twice as tall. A divided by 2, 2 over a. What is the area of this other pulse? And you say 2 over a times a over 2. That is 1 again. Okay, make it narrower even. 1/4 of width, but 4 times as tall. Well, in that case, the area is still 1. Let's say we take that process to the limit. We make the width infinitesimally narrow and the height infinitely tall, but making sure that the area under the curve continues to be 1. This thing. Integral from minus infinity to infinity of that function of time is 1. And we also know that for any point that is not 0, the function is 0. That is a very strange function. It is not defined the way we're used to. No, it's described by its area and by it being 0 everywhere but at t equals 0. That is indeed a very weird function, but a very useful one, and we'll be using that to sample functions we want to digitize. The delta function, the impulse function, has an illustrious history, right? The impulse function was introduced by no less than Joseph Fourier, and then it was advanced by Augustin Cauchy, Kirchhoff, von Helmholtz. Yes, Hermann von Helmholtz himself worked with the impulse function, and it was presented to us in its present day form by one of the fathers of quantum mechanics and quantum electrodynamics, Paul Adrien Maurice Dirac. That's why we call that the Dirac delta function, or sometimes just the Dirac delta. This slide does not really belong in this set, but it's there, so I will talk about it. For periodic functions, how do we find the Laplace transform? What we do, if we take the transform of the first period, f of t of s, and then we divide that transform of that first period by 1 minus e to the negative ts, where t is the period, and that is the Laplace transform of the periodic function of time with a period t, and with the first period having f of t of s as its transform. So far so good. We have introduced a whole set of functions, and you could say this is a second chapter or second part of the video. So if you're watching the video by parts, this is a good place to stop before we continue. But if you want to keep going, let's keep going. Laplace transform is a general transformation. It transforms a function of time into a function of s, right? It is also called an integral transformation because the transformation process includes an integral. That's why. What integral? This one. You take f of t, which is the function you want to transform, you multiply that by one other function that has one foot in our universe and another foot in the Laplace domain universe. Why do I say that? See that e to the negative st is the function of both t in our universe and s in the Laplace universe. And then to eliminate t, to eliminate time, you integrate from 0 minus to infinity along the time axis. That way t is gone and you're left with a function of s, your Laplace transform of f of t. From 0, eh? Well, actually from 0 minus, right? Right before 0. Why is that? Because that way we catch any singularity that f of t may have at t equals 0. That is why. By the way, this is called the unilateral Laplace transform. If you integrate from minus infinity to infinity, you would have the bilateral Laplace transform. But we are engineers and we care for what happens with the circuit after we close the switch. So for us, the unilateral one is the one we'll be using. Let's find the transform now of a few functions, because we will use them to construct a table that will be our lookup table. Transform of the unit step. Well, multiply u of t here by the e of negative t function, integrate from 0 minus to infinity. Yeah. And then we say, well, from actually after 0 minus, that is from 0 to infinity. Before 0, it's u of t is 0, and then from 0 actually to infinity, u of t is 1. I'm left with this integral, right? Integrate that exponential from 0 to infinity. But you and I remember what was this integral, right? The integral of e to the ax dx was just the exponential divided by a, the coefficient of the numerator of the exponential. So what we need to do is divide e to the negative st by negative s. That's what we do. Divide this by negative s, and then compute in the range from 0 to infinity. Let's see what it is. At infinity, this exponential with the negative exponent will have a value of, tell me, 0. And at t equals 0, the exponential is 1. So we say 0 minus 1 over s, that is 1 over s. That is the Laplace transform of the unit step, 1 over s, which we write, by the way, this way. U of t is a inverse transform of 1 over s, or 1 over s is a Laplace transform of u of t. We have our first transform, ub. Another one, transform the exponential. Should I say the decaying exponential? Not really. So this is our function, e to the negative at. What is with the u of t piggybacking there? Is that why you see e to the negative at begins at minus infinity, and we don't want that. We want that to be 0 before 0. That's why we multiply that by u of t. That is what we're transforming, right? Multiply by e to the negative st, integrate from 0 to infinity, and then what? Well, actually, from 0 to infinity, the unit step is 1, right? Yeah. And that unit step, 1, we can move it out of the integral. And then the multiplication of two exponentials, right, is just the exponential of the sum of the exponents. But we've already been here. We know how to integrate this. We know how to find the Laplace transform of that exponential, right? The integral is 1 over negative s plus a multiplied by the exponential and evaluated from 0 minus to infinity. Again, at infinity, the exponential is 0. At 0, the exponential is 1. 0 minus 1 over sa, 1 over sa. So the Laplace transform of this exponential e to the negative at is 1 over s plus a. Very simple and very memorable. It's easy to remember, right? Exponential that decays with the time constant of 1 over a has a Laplace transform of 1 over s plus a. We write that in the notation as this function of time has this Laplace transform. Are you still awake? Okay, let's take a break, right? A break that will take us all the way to Euler's formula, this formula. But we're going to write not one but two of those Euler's formulas. One for e to the negative, one e to the j omega t and another e to the negative j omega t. You say, what are you going to do with them? I'm going to add them together. When I do that, bam, I cancel out the j sine omega t. I get that the sum of those two exponentials is 2 times cosine omega t. What are you going to do with that? I will divide by 2, because this way I can write a cosine omega t as the sum of two exponentials. Oh, that's very nice. I have no idea why you want to do that, but I'm still nice to say, oh, that's very nice. Can you do the same for sine? Think about it. If you subtract this exponential by this one, the cosine will cancel out and divide by j2, and you get the sine omega 2. Let's use that. Let's find the Laplace transform of the cosine omega t of this one. Sure, you know there is a u of t multiplying that and all that jazz, right? This is a cosine that is 0 before t equals 0. Let's substitute that cosine by the sum of those two exponentials according to the formula we obtained in the previous slide. And then this integral becomes the sum of two integrals. This one for the first exponential, this one, and another one for the second one. But we know what to do with them. We've done that. This is just what? 1/2 1 divided by s minus j omega, right? The first one. Yeah. 1/2 s divided by s minus j omega, and this is 1/2 s plus j omega. We have seen how to transform them, right? Let's factor out 1/2. Let's simplify, and this is what you get. S, the Laplace complex frequency variable, divided by s squared plus omega squared. Omega is the radians per second frequency of the cosine in the time domain. That is the only place where it appears, right? Oh, that's very sweet. Cosine omega t becomes s over s squared plus omega squared. Oh, yes, it does. Can we do something about this sign as well? Well, sure we can. Transforms the sign. How do it? Well, we begin this way. We do exactly the same. We replace the sine omega t by this subtraction of two exponentials. We perform the integrals. Oh, observe j omega. Sorry, j2 and j2 down here. No problem with them, right? So I do exactly the same. But when I do the whole operations, the j will cancel out and I get it is omega divided by s squared plus omega squared. Very similar, right? The difference between the transform of the cosine and the sine is that the sine does not have s here in the numerator, and the cosine has an s on the numerator. Before we proceed with the ramp, I want to ask you a question. Do you remember integration by parts from your calculus courses? You don't? You do? Something like that? If you could break the integrand, into two parts, u and dv, a perfect differential, then that integral was the product of u and v minus an integral v of du. Remember that. Let's try to use that when in the transformation of the ramp r of t. We're transforming that from 0 to infinity. You say 0 minus 0, 0. T e to the negative st dt. Well, are you going to use integration by parts? Yes, I am. I have to identify which is a convenient u and the convenient dv. I should identify dv that is very easy to integrate. Well, look, integrating by parts, I choose dv as all of this part because that is very easy to integrate, and u will be just t, which is very easy to differentiate. If this is u, du is just dt, right? And if this is dv, v is just the integral of that you and I remember what it is negative 1 over s times the exponential. We've been using that all along. And then what? And then you use the formula for integration by parts. This integral will be u v, that is negative 1 over s multiplied by t exponential of negative st, and evaluate that in the range from 0 to infinity, minus the integral of v du. Well, minus times minus, that is plus, the integral of, well, 1 over s is not a function of time, so that can leave the integral, and you're left with just e to the negative st, which is an exponential. You know how to work. Let's work on this term here. At t infinity, this infinitesimally small exponential really overpowers the growing ramp. We have seen that in another functions. T times this exponential at t infinity is 0. You say, how can it be? At t infinity, t is infinite. Yeah, but e to the negative t is infinitely small. Well, it has been proven that the multiplication of them tends to 0, not to infinity. So this term is 0. And at t equals 0, t is 0, so this will be 0 at infinity minus 0 at 0. And you're left only with this one. 1 over s. What is the integral of this thing? You say, this integral is just what I had when I was trying to find the Laplace transform of the unit step. So this is the transform of the unit step, 1 over s. So 1 over s times 1 over s, that is 1 over s squared. And that is the Laplace transform of the ramp. 1 over s squared. What a lot of words for that, right? Ramp transforms into 1 over s squared. Let's review the ones we have. The unit step, 1 over s. The ramp, 1 over s squared. The cosine omega t, s divided by s squared plus omega squared. The sine omega t, omega divided by s squared plus omega squared. Anything else? Let's transform that impulse function, the Dirac delta, the delta of Dirac. We integrate short from minus infinity. There should be a minus infinity here, so please let me add that there. From minus infinity, no, from 0 minus. Let me integrate from 0 minus to infinity, right? You say, the function delta times e to the negative t. You say, well, you see, after 0 plus, at 0 plus and after, this integral will be 0. So that integral is non-zero from 0 minus to 0 plus. Sure. Well, then let's integrate that from 0 minus to 0 plus only, because after 0 plus, the impulse is 0 and the integral is 0. So we're going to integrate that between 0 minus and 0 plus, but at t equals 0, this exponential is 1. Being a constant, we can take it out of the integral like this. This is 1, you see in here. And we're left with the integral of the impulse function from 0 minus to 0 plus. And you know what is the value of that? That is 1, right? 1 times 1, that is 1. So the Laplace transform of the Dirac delta is 1. This is amazing. The impulse function exists at only one point in time, t equals 0. Not a microsecond before, not a nanosecond after. But when you go to the Laplace universe, that impulse function exists everywhere in that universe and has the same value, 1. For every frequency in the universe, the Dirac delta has it and has the same amount, 1 for that. That is super. This is a very interesting function of time. So we have now a Laplace lookup table, right? It's partial, right? It's what we have so far. We have the impulse function. This should be d of t. The t is not very clear. So the transform is 1. U of t, the Heaviside step function, 1 over s. The ramp function, u of t. So remember, we pre-multiply by u of t to make sure that the function is 0 for t less than 0. The ramp, 1 over s squared. The sine omega t, omega divided by s squared plus omega squared. Cosine of omega t, s divided by s squared plus omega squared. Yeah, I know it's omega now, but I'm lazy. I prefer to say omega. Now, before we end this, I want to tell you something. If you do this reading assignment, you will be in perfectly good shape to continue the course on electric circuit theory, analyzing circuits in the Laplace domain, even if you have not taken the previous math course on Laplace transform. So from the textbook, the Alexander and Sadiku textbook, Fundamentals of Electric Circuits, edition 5 or edition 4, exactly the same section, the sections of the same chapter and the same pages in edition 4 to edition 5. Read sections 1, 2, 3, and 4 of chapter 15, which is between pages 675 and 697, and work out the corresponding end of chapter exercises. Many fine exercises there. Also, I am not done. More reading. From the textbook of DeCarlo and Lin, Professors DeCarlo and Lin, Linear Circuit Analysis, read sections 1, 2, 3, 4, and 5 from chapter 13 between pages 493 and 508, and work out the corresponding end of chapter exercises. You do that, you will be fine for the next chapter on solution of circuits in the Laplace domain. And now, so that I can leave you with a smile like the ones that Mr. Schultz put on my face as a child. I leave you with that little cartoon. Freeze and read. Thank you very much for your attention, and I hope to see you all in the next video. Let's go now into a little Easter egg. The calculator I showed you during this video is the famous HP 35, the very first scientific calculator. I had one of the first few that was sold. It was not a cheap calculator. As a matter of fact, it was extremely expensive. It ran for $395 American dollars at the time, back in 1972. When Hewlett-Packard asked the marketing company at the time how well that machine would sell, he was told, the machine will not sell. Nobody will buy a calculator that expensive. Hewlett-Packard determined that if they sold at least 10,000 calculators, they would recover the cost of design and production, right? You know how many calculators they sold? Because they went ahead and produced it and distributed it. 100,000 calculators the first year, and 100,000 every year of the 3 years that it was on production. In 3 years, from 1972 to 1975, it sold 300,000 calculators. Mine was one of them. I remember the amazing feel of opening the package of my brand new scientific calculator. It was a memory that I treasure. And now, how expensive was that really? Well, I went to a website that is called Measuring Wealth, where economists use many parameters to determine what would be the equivalent amount of money in different times. And I asked the website, well, if I have $395 in 1972, how much money would that be today in 2015? And it said could be anywhere, depending on the parameters that you choose, between $2,200 all the way to $5,000. I'm being conservative. That calculator would have cost today $2,200, and it was a calculator that had only the 4 basic operations: plus, minus, multiply, and divide. It had 1 memory storage, the 3 trigonometric functions and their inverses, an inverse key, a square root key, and what else had the square key, and it had the 2 logarithms, the 2 anti-logarithms. That was all, and it was amazing. Anyway, that's all for an Easter egg. I hope you enjoyed it. Thank you very much.